The geometry of the substitution method for integration, a brief introduction. Our objective is to demonstrate how a substitution in integration reconfigures the integrand and the limits graphically. Some materials for review include the substitution method for integration, specifically the conditions, how to graph functions, and of course the substitution principle from algebra. The substitution method for definite integrals states that if g prime is continuous on the closed interval ab and f is continuous on the range of g of x, then the integral from a to b of f of g times g prime dx will be equal to the integral from g of a to g of b of f of u du. And this rule states that when using a substitution in a definite integral, we must put everything in terms of the new variable u, not only x and dx, but also the limits of integration. The new limits of integration are the values of our new variable u that correspond to x equal a and x equal b. And remember that u is being substituted as a variable for the function g of x. So let's consider the example here. Here we have the integral from 1 to e of ln of x divided by x dx. The graph in the original plane of x's and y's looks like this to the left, where you have a curved shape coming in where you have ln of x over x. And here we're finding the area under the curve from x equal 1 to x equal e. But when we make a new substitution and let u be equal to the ln of x, our integral actually becomes the integral from 0 to 1 of u du. So in the u plane, we have, in the u f of u plane, we actually have a straight line integrated from 0 to 1. And this is one reason why we do substitutions, is to see if we can make a kind of complicated curve look more manageable and for us to find the area under. So the integral from 1 to e of ln of x divided by x dx is equal to the integral from 0 to 1 of u du, and both of those integrals equals 1/2. But here we're using that u is equal to the ln of x, and du equals dx over x. And that's from the chain rule. So what we've established here is that the areas under these curves are the same. And that's because the substitution allows us to examine the graph under a different scaling. So on the left here, we have our standard looking graph. In other words, we have the graph in the xy plane. And here we have the function coming in from 1. It curves up until we get to e, which is about 2.71828. That's what this vertical line is here for. So we're finding the area between 1 and e under this curve. But when we do the substitution and we have f of u equal u, and we let u be equal to the natural log of x, what that does is it changes this curve into a straight line. And the x variables, this 1, 1.2, 1.4, 1.6, etc., are now put on what's called a logarithmic scale, where we have the ln of 1, the ln of 1.1, the ln of 1.2, all the way up to the ln of 1.8, and then further all the way up to the ln of e. So not only did the curve that we're trying to find the area under change from this ln x over x to essentially a straight line under this new scaling, our x-axis, our input axis, went from 1 to e. That was changed into ln of 1 to ln of e. And we know that the ln of 1 is 0 and the ln of e is 1. So this is what is happening when we do this substitution. We're changing the variable that we're integrating with respect to so that we can take complicated curves and kind of morph them, if you will, into more familiar curves. And the input axis is having a rescaling done as well, so that when I do morph this curve, the input axis and the output axis still operate under similar restrictions. Let's consider another example. Here we have the integral from 1 to 3 of x times the square root of 9 minus x squared dx. The graph of this is on the right, and here we can see that the total area under the curve is 9. When I make the substitution that u is equal to 9 minus x squared, we end up with a new integral from 0 to 9 of 1/2 square root of u du. And we see that we have the same area under this curve as opposed to x times the square root of 9 minus x squared. The areas are the same, and remember, that's what we're trying to find here. So what happened is that the original curve that's pictured on the left here, what we've done is we've kind of grabbed that right side and we've stretched it all the way out to 9 and kind of pushed the bump down a little bit so that it resembles a square root curve, in this case 1/2 square root. And essentially what's going on here is when we take this morphing of the curve, when we do the substitution and we morph the curve, we actually end up with an easier curve to find the integral with, because we have the standard rules for integration. So we've taken a complicated function and rewrote it in terms of a simpler function by changing the input scaling and the curve itself as a result. So here, under the standard denotation in the plane with x's and y's on the left here, we have 1, 2, 3, we have 1, 2, 3, 4, and we see that we have this x times square root 9 minus x squared curve from 0 to 3. But when I did the substitution that I let u, this new variable, be 9 minus x squared, that essentially enabled us to go from 0 to 9. And under this new scaling, this kind of bending curve here on the left got stretched out into a square root looking curve on the right. And I'm able to find the area under the square root curve because that's a standard power function with 1/2 as its power. And we have a rule for integrating power functions relatively simply. So the substitution principle states that using one form of an expression over another does not change the validity of the statement. And therefore, when we use a substitution, this may allow for easier algebraic manipulations, especially when computing integrals. So geometrically, the substitution will act as a transformation. It changes the description of the xy plane, and it morphs the curve into a format that is conducive to our algebraic tools, such as the power rule or the exponential rule or using trigonometric rules. Thank you for your time and attention.